Hi, everybody. How are you doing? Okay, great. So let me post the code information. If you can check out Canvas and download the lab. We'll start in a few minutes. Hi, everyone. How are you doing? If you just join us, check out the lab. I just posted the code right now, so I'll go over the code. We'll start in a couple minutes. If you wanted to open your LC3 editor and simulator, I had to take it into 2 image, so it's a little longer today. So today we're going to work with JSR. Okay, so we'll start in 1 minute. So please download the lab and look it over. And I just posted the code on the lab page, but I'll go through it now. Okay, since it's 6 o'clock, we're going to get started. I'll get into screen share here. Minimize everybody. So this week we are going to work on the lab, and you can find that in CIS11. Tomorrow I'm going to try to update your grades. So if you have anything that you haven't submit, make sure you do that, and then I'll give you feedback when I go through them. So for the lab today, we are going to multiply and divide in LC3. So you can see how that's done. And again, this is a lab that's used from the lab manual for the university manual. So in the problem statement, it tells you that you are given two integers, x and y, and you want to compute them by doing multiplication. So you would have a product of x and y, and then you would have x divided by y, in which you would have quotient. So you're going to do integer division, and then you're going to do x mod y, which should be to receive the remainder as the output. So your input would be x and y, and keep in mind that in the statement it asks us to put x and y at location hex 3100 and hex 3101. So this is where we're going to set the values. Then in the output, we are going to look at the result for x times y, and the result for quotient, which is going to be x divided by y. And remember that when you divide, if you divide evenly, then you're going to get a quotient. If the number doesn't divide evenly, you're going to get a quotient and a remainder. So for example, if I have x is 5 and y is 2, I should have 2.5, right? So you should have a quotient, which is 2, and the remainder is going to get stored in the mod area, okay? So when we set this up, these two areas are the location where we would get the output for the division. And those are at location 3102 and 3103 and 3104. And it says that if x and y inputs are invalid, so we need to check for validation there for x divided by y and x mod y, then we need to refer to the section 5.2.5 to look at the details, okay? And place 0 in both of the locations for 3103 and 3104. So if it is invalid, the output would be 0. And that is the requirement for input validation. Do you have any question for me regarding the problem statement? So this lays out what we need to do for the program. And in this program, we're going to work with subroutine, which is equivalent to functions in C++. So subroutines would be what you would see in C++ as functions, and it would form a group of code that is intended for, in our case, multiplication that would be used multiple times. So you can define your functions and then call that function when it's needed. And we are going to use this approach, and then next week we are going to do another multiplication program very similar to this, but we're going to make it more efficient. And subroutines are to be perform a logical task by the OS, given the parameters used with them. And at the end, they return one or more results. So in a function, when you write a function in C++, you want to return from that function. And in our case, it makes perfect sense because when we write multiplication, division, and mod functions, we want to return the values from those functions. Okay, so in this week, we are going to work with functions. So if we're looking at an example, if our function is f of n and f of n is 2 times n plus 3, we want to put n at a location and f of n is stored in a subsequent location, very much like what we seen last week, right? We have the n value in one location, that's where we set, and then the subsequent location is where we would have the output, which is f of n. Your register 0 is used to pass the parameter n to the subroutine, and register 1 is used to pass the return value f of n to the subroutine to calling the program. So you can designate the register, and we would start with register 0, where that would be n. Last week we used register 1 for n, right? So in this example, they tell you that you can use register 0 to pass the parameter for n and register 1 for f of n. Then when we use JSR, this is when we would have the execution transfer. And in JSR, we want to save the return address. So what it's doing is it's saving the return address, which is the address of the instruction that follows the JSR. And that will be in register 7. Okay? And it tells you to look at the figure 5.1. Subroutine would end when you use RET, which stands for return from subroutine, very much like how you use return in C++. It's simply, when that happens, when you use RET, it simply assigns the return value to register 7 to the PC. So by default, it uses register 7 for the return process. Okay, any question?
So RET is basically the same as JMP, but specifically R7?
Yes, but with that, it actually does the jump with the store. Okay. So JSR stands for jump to subroutine, and that's when it's exactly like how we would call functions, right? In C++, in the main, you simply put the function name. So in our LC3 program, when you want to call the subroutine, you want to put JSR and then the label for that subroutine. And we would use the label when we define that subroutine. Okay, so here we would see that there are 2 subroutines in this example, like what we've seen with the f of n is 2n plus 3. And what you have is we have one subroutine called f, okay? And in the f, we would use it as the label, and the definition for that subroutine, the instructions are listed there. Okay, so we can go through this real quick so you can see. LDI R0N, this is to load N to R0. That's what they mentioned here in this bullet. And you, instead of this, the top section where you do the JSR, you wanted to do it at the beginning, because when it hits that line, it's going to say, oh, jump to subroutine, whatever the label is. So when it gets here, it's going to go to F and it's going to execute this. Okay. It's like how you would have the function call in the main. So in the main, when it gets to that line, it sees that function, right? And then it's going to go to the function definition to handle that. So here is at the beginning, we want to say JSR and our subroutine, so that way it's going to go to that section and it's going to execute the instruction in that section. Then after it's doing that, after we have the return here, we want to be able to store it because that's the output, right? So if you're doing multiplication after it, you're doing add subsequently in all those lines, you return from that. What you want to do is you wanted to store it to the output location. So in the subroutine F here, we clear R1, like what we had asked to be set up with R1 here. We have R0, whatever N is, we're going to add that with R1. We're going to add it to R1. So we put N, we copy N to R1. And then we're going to do an add again, because remember in this one, it's 2N. So how do we represent 2N? We first add the N to R1, that's 1N. And then we add it again, right? Repeatedly, that gives you 2N. So these two line represents the 2N here. Then after that, we would add the hex 3 to add in the second part of the function. So recall that all the other labs that we've done and all the exercises that I've walked you through, we take the function or the equation and we piece it into subtasks, right? So these two lines represents the 2N because you add the N from register 0 and you put it on R1 and then you add it again so that way you have 2N. Then after that, you're going to add the 3 so that way it, at this point at this line here, it becomes the R1 stores 2N plus 3. Then you're going to return. And after it finished this, when it hits the return, it stops that subroutine and it's going to come back to this line and it's going to store register 1 because that's where our 2N plus 3 is, to F of N. And then we halt, and then the rest is filled. So as you can see, this is an example for this function. So we're going to do something similar to this today. Okay. Any question on this? Okay. So now when we look at the flow chart or the steps for this, right? So in step 1, when you do the JSR, we would do the JSR plus 1 because it needs to increment in the address location. Okay. And then at this point, the IR is going to store your subroutine and register 7 is 0. Okay. So, and then in step 2, it's going to have it already have the subroutine address plus 1. It's already incremented by 1. IR is going to be having the JSRF. And then in step 2, it's going to copy PC to register 7. So that way it would have the address for the return instructions. Okay. And then in the next step, the subroutine address is then in PC. And how is that doing that? Because IR is going to load that address to the program counter. And that's how it's able to execute that function or that subroutine. And then since we have the return already, it's going to have the address of that subroutine plus 1 in register 7. So that means that it copy the subroutine address from IR to PC so it can execute the actual subroutine. Okay. So this is what's happening with the simulator when you load it and run it after you set your value. Okay, remember we have to set value today before we run. Next, we're going to talk about saving and storing register, and this section is important because we will keep using this method or this approach from now on. Okay. So it tells you here that make sure at the beginning of your subroutine, you save all your register that will be destroyed in the course of the subroutine. Before returning to calling program, restore, save, register, and that's important. Why is that? Because if you don't, you're going to lose your value. Okay. So how do we save register? We simply store, right, to a label temporary, and we're not giving that label any address at all. We can use hex 0 with that. So think of it like a temporary location in the memory that we use, so that way we can actually store out some of the value as it does a calculation. Otherwise, it's going to get overwritten in the register. You cannot use register to keep stacking up the value, because as it updates with the parameter, it's going to change that. So this is how you would save. So here, let's say that in this section of our code, we would do a store, register 5 and 6, and that's a common approach in LC3, is you would use the later register like this, and you would give it a label, save register 5, save register 6. So when you enter the subroutine, you need to store it, okay, to 5, from 5 to the location, from register 6 to the location. And then when after you store, you have to load. Remember, they go hand in hand. So if you start with store here, later on in your program, you have to load them, right? You have to bring them back. So when you restore, you simply just do a load with the register from those labels, and you can fill them with hex 0. Okay, so this is an approach to how you would store and restore register. And we will incorporate that in our program. So overall look, right? If we're looking at how we would do the subroutine, so first you're going to have the multiplication. I have a chat question. Store and restore within the same subroutine. Yes. So you are going to have to do store and restore. I will show you shortly. Okay, hang tight. So here is where we would call the subroutine. You do a JSR jump to subroutine. So you jump to multiplication. It's going to go to the multiplication. We're going to do the calculation here. We're going to return, right? And then next we are going to do the division. Then it's going to go to the division, do the calculation, then return, then we halt, and then we end the program. Okay, so that's like a general layout on what's happening. So you need to do the JSR at the beginning, so that way it can go to that section, and it's going to do the definition of your subroutine, and it's going to do the instruction there. So in here, Lewis asks, is that going to happen in the subroutine of store and restore? Sure. First, you got to save the register, otherwise it will be overwritten. Then you have to restore it in that subroutine. And you can reuse the same approach in the other subroutine. So it needs to be done in the definition of the subroutine, or the definition of the function. That you need to save register and restore register before return. Got it? Any question? And understanding this, looking back into Java or C++, it makes a lot more sense, because you're going to say, oh, the compiler handles that, right? Because when you type in return, well, right, it handles a lot of the back processes already, like save and restore register. But in assembly, we have to manually work with that. Any question? Okay, so let's talk about multiplication. Okay, I touched on this already in the lecture, but I want, and also earlier when we look at the example. So really multiplication is addition at many times. So when you have x times y, it's really x plus x plus x, y times, right? And so when you look at the pseudocode and it's nice that they already give you this, right? Because you can just take this and translate it to LC3. So when you're multiplying x, y, the product is in the variable prod, x prod y, right? So keep in mind that you could have a sign value like negative x or negative y, right? Those are your input. So we need to think about how the sign product would be, because if it's negative, then if x is negative, then x is less than 0. So if x is less than 0, then x is negative x. So with negative or sign, what do we have to do? To complement. Okay. And so we need to convert x to positive, because in the system, what it sees, it just be a 2 complement of that value that would represent x. So sign is equal to negative sign. Then y could be negative. So if y is less than 0, then we would do the same thing, convert y to positive. And then we would handle that. And remember, the rule with positive and negative in integers is that if you have one input that is positive and the other input that is negative, if I have positive x times negative y, I'm going to have a negative result, right? So here is where you need to handle that, right? This section right here. If I have any of the input that is sign, when it's less than 0, then my product is negative. Okay. And we want to have the while, because the do while, because it says while y is not 0, do this. Because if y is 0, then our output is 0, right? Any of the input is 0, then we would have a 0. Okay, so just this represents the multiplication rules in general. So this has to be established in your code. Any question with listing 5.4?
Is the reason we converted a positive because the program can't take the negatives, right?
Yeah, it
And
doesn't
so
understand. Mhm.
if we multiply two numbers, it disregards the negative, right? But we can always just throw it back in the
Right,
end.
at the end, that's correct. You have to
Okay.
manipulate it that way. Otherwise, because the processor can't tell the difference, right? It's that's why we learn to do two's complement, is because we would use the representation of sign value to show the two complement or the negative value. Okay, so one thing before I move on to the next section, parameter of x and y are passed in multiplication for the subroutine, and we want to use register 0 and 1 like what we've seen, and the result would be in register 2. So that kind of set up already which register that we need to use. And then you just follow this algorithm, this requirement, these conditions, I should say. We have to implement these conditions in your code. Okay. All right. Next, we're going to talk about division. So in division, what we're doing is, like I mentioned earlier, when you divide, you would have a location that's going to store the quotient and a location that's going to store the remainder in the case that it doesn't divide evenly. Okay. And so when you look at a calculator, when you punch in, right, you have a quotient that's going to be the whole number, and then the decimal points or the remainder that's going to show subsequently. So when we look at that, we would have to use mod, because mod is going to give us what's remain. So when we have x, we would have x is equal to x divided by y times y plus x mod y. Okay, where x divided by y, this section right here represents the quotient, right? So if I take 5 divided by 2, I get a 2 as a quotient, and then I have a 1 as a remainder. So this section here, this x divided by y is a quotient, and x mod y, this right here, is the remainder. Okay, so the example that we have here is if you have x is 41 and you divide it by 7, right? If you look at that and break it down into really small pieces, that's 5 times 7 plus 6. Okay, so when you take 41 divided by 7, that's 5 times, right? And you have 6 left over. That's 6 as the remainder. Okay. Any question with this part? Because if you see it clearly, then it's easy to really put it together. Then here, then we want to compute both quotient and remainder. So the parameter x is passed through the div, which is through R0. So we're going to have a subroutine called div, and we would use x would register 0 and y would register 1. Okay. And with the subroutine div, it should check for the conditions like what we said earlier. If not, it should return with register 2 as 0. So anytime that when we cannot divide by 0, so y has to be greater than 0, right? You cannot divide something by 0. That's just not the rule. So y has to be greater than 0. So we have to implement this criteria as a condition. Then if not, it should return register 2 as 0. So when you're trying to divide by 0, right, it should validate that, and it should say, oh, when you divide that by a 0, no, that's an error. So it's going to put a 0 in the output. Okay. So here it says if they are satisfied, then register 2 is going to be 1 to indicate the results is valid. Overflow condition need not to be checked this time. And the figure 5.2 summarizes the input arguments results and then what should be turned. So when we do register 0 for x, x divided by y, or 0 if invalid. So if it's invalid, then it's going to be 0. Then register 1 is going to be y. So when we do x mod y, 0 if it's invalid. Register 2, 1 if the result is valid, otherwise 0. So if we have a valid result, register 2 should store 1, and otherwise it should store 0 if it's invalid. Okay. Make sure that you remember this, because when you go through the program, you're gonna see, oh, that's a 1 if it's valid, it's a 0 if it's invalid. Okay, now here is the condition for the division. Okay, that's your pseudocode. We initialize the quotient, so we need to clear it, right? Whatever register that we're using, and so we would have initialization here and initialization for the remainder in case it's invalid. Then we would initialize valid with 0. If x is less than 0 or y is less than or equal to 0, exit, because we cannot divide by 0 or anything less than 0. We want to validate that. Then we would have valid is going to be equal to 1 because we said that, you know, that's where register 2 would have a 1 if it's valid. And we would then have a temporary location where x, it's going to hold what's the quantity or what's left for x. While temp is going to be greater and equal to y, do temp and temp minus y. Okay. So if it's valid, then what we're going to do is we can take whatever the value in temp, and it's going to be, we have to check with the do while that temp has to be greater and equal to y, and then temp is going to be temp minus y. So when we subtract that, we're going to have a quotient, okay? And then the +1 is where we would put the, for the next one, we're going to put the remainder or the temporary for the remainder into the remainder. Okay. So when you divide, you get a quotient. So you put it in the quotient, and then in the remainder, we would have another area in the memory for the remainder. Okay. Any question with this? So you're going to see this in the code today. So what I want you to do is write the program. And the way that you would do this is, ideally, we should do the multiplication. You can check it by itself, and then you can add in the division. But since I have one session with you today, I'm going to do it together, and then we will assemble the program as a whole. Okay. But if you do this manually, let's say for your project, you have to write your program. I think you should, what you should do is you should write your subroutines and test your subroutine and see, you know, and then you can add on the next subroutine and then check. So that way it's easier for you to troubleshoot in case you run into a problem. Okay, so write the program. I want you to run the program, give me screen capture of your code and the test of your input and show your output. So when you test, I need you to test what x is 10 and y is 7. I need you to have a second test, 29 divided by 55. Notice that it is less, right? X is smaller than y. And I need you to test 11 and -12, and I need you to test 14 and 0. And remember, you need to test with hexadecimal value. Okay. And then I need you to provide your screen capture for your test. And I need you to answer the questions. Do not disregard the questions. I will look for the answer on what you put. So what are some of the key points you've learned in this lab? Okay, so just don't have to write a lot, just summarize some of the things that you got out of the lab. What were the challenges that you come across? Something that's not clear to you, something that didn't work, right? I basically am going to walk you through the code, so it should work. I tested the code. How can you apply subroutine in future program or exercises or project? Okay, and I will look for subroutine when I grade your project and your future program. So we have to learn how to do this today. Any question? Okay, so our code already addressed this part, A through A through G, okay? And it also gives you clues, excuse me, like choose complement for the sign value, that what we talk about, you need to use labels for your subroutine, etc. So we already addressed A through G. The only thing that you need to test is you need to test your division program and your multiplication program with the values, right? As it combines. So you need to test your multiplication subroutine and division subroutine in your program. Okay, remember they're in separate locations, okay? All right, any question? Okay, with that said, I posted the code, but I'm gonna go over the line of code. Okay, so this is the first image that was posted on the lab. And so you would have the origination address at text 3000 like always. And then we are going to load X to register 1. So we are going to do an LDI X register 1. My dogs are so confused. Sorry. Now they want to stay inside. All right. And then we are going to do a load for Y to register 2. So you see that in the comment there, that Y is in register 2. Then after you load, you are going to jump to subroutine. So we have a subroutine called for multiplication. So we would call that subroutine there. So multiplication subroutine. Okay, so far so good. So at this point, what the program is going to do is it's going to go here. Okay, and then after it does its thing here, then it's going to come back to the next line, which is the store. Okay, so after we calculate the multiplication, then we're going to store register 3 to X times Y, or XY. So the product XY is in register. We store it from register 3. So it's going to put it onto the XY location. So that takes care of the multiplication. So think of this as like the main in your C++ program, right? And this is where you call the multiplication function, okay? And you also declare what XY is, right? And then after we finish with the multiplication and we store the product out, then we're going to call the division function, or we're going to jump to the division subroutine. So JSR div. And in division, we remember we said that there's the quotient and there's a remainder. So we're going to do to store. We're going to do store from register 5 to quotient or quote. And then we're going to store register 3 to R for remainder. You can call it whatever you like there, but we try to stick with the common name so it's easy. Then we're going to halt. Okay. So now we're going to get into the function definition and the condition for each function. Any question with the first part of our code? Okay, then now we are going to start the multiplication subroutine. So we have a mult, and you can keep it on the same line if you like there, okay? Remember, we have to start with storing the register. So it ties it with that label. Okay, and that's important. And then we have to restore it when we're done. So, sorry. First, we're going to save register 5. So we're going to do a store register 5, save rec 5. Then on the next line, we do the same thing for register 6. Store register 6, save rec 6. And then we are now going to handle the arithmetic, right? And the conditions. So here, I'm going to copy Y from register 2 to register 4. Why am I doing that? I don't want to use register 2 and change register 2 because I'm going to use XY for division. So I want to copy it. Okay, so here I put Y onto register 4 by doing copy. Then we are going to invert and start the 2 complement. So here we do a not for register 4, and we're going to add a 1 so that way it gives us negative Y. Okay, and this is where we're going to check for positive for Y. Y is greater than 0. Okay, so at this line, we have what? Register 4 store represents negative Y, right? So here is where we're going to branch positive, and we're going to go to pos loop. Okay, and we'll come to pos loop later. So what it's doing here is for the negative values that become positive, right? It needs to check. So we need to check for the negative values that become positive. So it needs a negative counter instead. Okay. Because remember how we were using in the pseudocode, it talks about sign, right? And how we wanted to be able to use that. So here is where we're going to branch it for positive, check it for positive. All right, next we are going to check for input validation. And so we have a loop label. We are going to use register 6 because we have previously stored that. So register 6 and register 5 and register 4. So we took, right, what Y was in register 4 when we left it last time. That was what we did, the 2 complement. So whatever in register 4, we're going to add it to register 5 and register 6 and put it on register 6. So here is where we would check for n is greater than 0. If yes, it's going to go to quit. So here is where we would branch for 0 and positive. So it's going to check whatever's in register 6. If it's 0 or positive, it's going to quit. Okay. And then we need to increment the counter. So we need to loop up. We count up +1. Remember how in the flow chart, it shows you that you need to have a +1. So that way it would go to the register 5 location plus the 1. Nothing yet. So Register 5 is just the address, is the value, which is hex 0 when we look at the fill at the end. It's a temp location. Okay, you guys have to think about that. Think of it as a temp location, and that's it. Okay, so nothing yet. Any other questions? So when we check, when it's greater or equal to 0, we're going to go to quit 1, right? If it's not, then it's going to go to the next line where we're going to increment the counter. And we are going to multiply until the loop hits 0. Okay. So here is where we do an add R3, R3, R1. And what's R1? Rx. What is R3? Right? So let's see, nothing yet, right? Because here is where when you store, that would be later on after the division. So when you store, that will be after it. So R3 is going to have our output. That's what we're going to have. And we are going to multiply until it hits. So it keeps looping. And so when it does that, it keeps going. So you're going to branch back to loop. You're going to force it to loop. So it's going to come back here. It's going to do that again. And it's going to multiply. And it's going to multiply. When it's done, right? When it gets to the 0, then we are going to return. Okay. So when it hit, when it hits 0, right? Because we check for 0 positive. That's why I put here when counter gets to 0, when we check for 0 or positive, then it's going to go to quit, and quit is going to force it to return a value. Okay. And earlier we have a branch positive for pause loop. So in the pause loop, and so what we're gonna do, 0, we're gonna have the y, which we had in register 4, and then we're gonna add it with the 0. Okay. So just when you add something with the 0, does that change any value, right? So basically we just recopy it. In the second loop, in loop 2, this is where we would use, it's repeated from the top one, right? But what we wanted to do is we wanted to check for y is negative. So in the second part here in loop 2, what you're going to do is, I put here that it is the same as the top one, but it makes the value at the end negative because it had a negative value of y. So the result must end up with a negative. So when you have like a negative y, right? When you multiply, you would have a negative output. So we want to check for when y is less than 0. So you're going to see very similar code to the last one. We just use a quit 2. So what it's going to do is it's going to enter the loop, right? And we're going to add it and put it into a register 6. And when it gets to the 0, it's going to loop until it gets to the 0. We no longer check for 0 or positive because in this one, we wanted to check for negative, right? When it gets, we want to have negative output. So we're only going to branch it for 0. And once it hits the 0 as a counter, it's going to go to quit 2, where it would then do a 2 complement to show a negative value. Okay, this is how you're going to output negative value, a signed value. Because earlier we handle it with just positive, but it's going to return that, right? Because if you're looking at, let's say X is 3 and Y is -1, you're going to have a -3 as a product. So how do you do that? You're still going to multiply 3 times 1, which is 3, and then you're going to sign it by doing a 2 complement. Okay? So we are going to count it up. Then we are going to have it keep looping until it gets to 0. Then when it gets to 0, it's going to go to quit 2. Then we're going to do a 2 complement to make that number sign. Okay? That was in the pseudocode that we saw earlier. So we're going to make it negative. And then after that, because we stored the meaning, we have to load it out. So we have to restore it. So you're going to do a load R5, okay, and a load R6. And that would be just for the multiplication. Any question? So you saw this image is on your left page. Yes.
Shouldn't there also be a load R5 and load R6 with the quit 1?
No, because if you load there, you are not going to be able to use R5 or R6 in the following loop in the quit 2. If you load right here after the return or before the return, you cannot use it in to check for the negative multiplication. So the subroutine ends when you restore R6. Yes. And I cut off another line, which it does the return. It ends, Lewis, when it does the return. So what you want to do is you want to restore before you return for the last step, right? Because the return here is for the positive value, but you're still using R5 and R6 here. So if you load it out, then you have to store it again for the following loops, right? We don't want to do that. We want to be efficient. So when you return here, that's just going to be for the positive. Then you have to check the condition for the negative. So you would load it out before you return for the second loop for the negative. Okay. All right. So I'm going to bring up the other image now. Okay. Yep. This one's a little harder, right? So yeah, it got cut off, right? So after you load, you restore that out, you would then return and that complete that entire function, okay? But if we don't return in the last one, we're not going to have that positive value. And since we're still using register 5 and 6, we have to keep going and then restore it before the final negative return, okay? Then notice here that you have a fill because it's temporary. You don't need to fill it down here. You can put it right next to the section, what you're doing there. Okay. And then you want to, now that will free up, it will overwrite whatever in register 5 and 6 for the division method or the division function. Okay. So you can fill that right here. You're going to see this again. Trust me. All right. So that take care of our temporary location so we can return valid information or data. Next, we're going to talk about the division method. So first, we're going to check if y is going to be 0, because we cannot divide by 0. If it is, right, when we add it, because remember, register 2 had the y, right? That's why I copy it to register 4, because if you keep reusing register 2, that might change the situation down the line, right? So it's safe to do a copy. So here we initialize, right? We add the 0 to register 2 again, and that way we can check it for 0. So if it's 0, we're going to send it to quit 3, which force it to return, right, a 0 as the product in the product section or the output section. And then here is where we start our division. Okay. We're going to copy y to register 6, right? We already took care of the multiply part. So now we can reuse register 6. Then, so what, because we wanted to use register 5, 4, 3, and 6 in this area. So I copy it over. And then I clear register 5. Then I copy register 1, which is X, into register 3. And then I copy Y into register 4. There's a reason why we're copying. Okay, watch. Here is where I do a 2 complement of register 4, which gives you what? Negative Y, right? Okay, remember that Y is in 2 places, register 2 and register 4. X is in 2 places. The original X is in register 1, and the original and the copy is in register 3. Okay, now we're going to take register 4 and we're going to make it negative. Okay, with 2 complement. And then we are going to add X with Y, which is X subtract Y at this point, and store that in register 0. Okay, because division is a subtraction. Okay, now if it's negative, we're going to branch back into quit 2, which was in the other section. And that it kills two birds with 1 stone. Okay, so when we do quit 2, it's going to check if Y is greater than X. The madness. Okay, and if you're not sure, you can look back into quit 2, what it's doing there. Then loop 3, okay, we're going to count up and register 5. And in this section, register 5 now is what? We cleared that previously. Okay, and then we add the 1. Okay, so it's just a +1. And then we are going to do X minus Y, okay, and put the output in register 3. And then if it's positive, we're going to go back to loop 3. It's going to start all over again. If it's when the counter hits 0, then we're going to go to quit 3, which we're going to return. So positive, it's going to reloop. If it's 0, it's going to return. And if it's negative, it's going to add the result to Y. And if it's negative, then it's going to add the counter +1. Okay. And so here we do an unconditional branch back to or to quit 3, where we do a return. So that would make us back to calling the program. And the rest is your field location, like what the problem statement gave us. X is at 3100, Y is at 3101, XY is at 3102, quotient is 3103, and your remainder is at 3104. And the end of your program. Okay, question. And in this one, why don't we save register and store register? Well, we don't need to reuse it anymore after division, right? We don't need to restore anything after that. That's the end of our program. Earlier, why do we have to store and restore is because we are reusing those registers for the division, which is coming up right after. So that's why you have to, there's no magical place where the value goes, right? You have to make a space and put it there. And then so that way it doesn't get changed. Okay, so that makes it a temporary location. And so you can pull it later. Otherwise your data would be, it would be warped. It would not be correct. Okay, no question. So next week we are going to do a similar program, but we are going to make it better. Okay. All right, so after you have your program written, not too long, it's not bad. We're gonna translate, assemble, right? And then you can, like what we did with the lecture, we talked about the object file and the hex file. So now that you know that all those symbols, all the labels and the address that ties to those labels get put into this .sim. And then what you can do is you can load the program. Okay. And then before you start the program, right, remember the location, your XY is at 3100. So you are going to do a hex 3100 to set your value, right? I click this button right here. And I'm going to test it with not the one in the assignment that required, but you should test with what they ask in the assignment. So I'm going to go ahead and test it with a 3, right, for X, and then 3101. Remember that we did not control overflow, so when you get to the larger value, it might be a little funky. So I'm warning you because we didn't implement overflow on this one. Okay, so there's a reason why we used one of the test values larger. So all right, so I'm gonna do a 2. Actually, just do a Y as a 1, see what it does. Okay. All right. And then we are going to run. So after you run it, you're going to go ahead and jump to, and we want to jump to 3102 to look at the product, right? I have X as 3 and Y as 1. Okay, here's my X, here's my Y. I got the product as 3. And I got the quotient, 3 divided by 1 gives me a 3, and I have 0 remainder. So it checks out, right? Then you can use a different value. You can use one that has the remainder so you can see. So make sure that you set your value for, what's asked in your assignments. Remember, make sure that they're hex, not decimal. Wow, maybe I should extend the lab and make it a little bit longer because it's only an hour. But I want you to take your time and understand it. Come on, buddy, go inside. have 2 dogs and they keep making me opening the door for them and they take turns to punish me. Anyway, I love them. Question? Okay, so in this one, what we're learning in this one, right? You saw how we implemented JSR. And so we learned how to use subroutine. We learned how to use save register and restore register. So that way we can establish a temporary location. And we learn how to officially operate multiplication and division, right? Like what you've seen in the example in the lecture that's from the publisher people, I felt like it was super lacking. But if you're looking at multiplication and all the rules with the multiplication, you look at this lab. Okay. Where it handles, and you can try with negative value. Remember, you need to convert negative decimal to a hex and test with that. Otherwise, it doesn't know what negative hex is. Any concern, questions?
Oh, Professor, I have a question.
Mhm.
So I put an example like I put 6 for X and then 3 for Y.
Mhm.
And I think for the product, it gave me 12. And with the 12, would that be a hexadecimal or?
They are all hexadecimal. Your input, when you type X, that's a hex.
Got it.
Yeah. If your input is with an X, and simulator only understand hexadecimal. Anything above 9, right? You cannot have a decimal equivalent anymore. So yeah, we have to use hexadecimal to check. So if you wanted to check like negative 55 in decimal, you can convert it to a hex value and see what that would be. Okay. Now, like I said, we did not control overflow. So if you test it with a larger value, it's not gonna hold a very large value. Just keep in mind, because we're only gonna have the bits that the immediate value for the word is gonna be for the word size only. So
Got it.
when it reached the ceiling, at one point it's gonna reach a ceiling. So our program has limitation in that it's gonna reach that ceiling because we didn't control the flow. Then it's gonna, we didn't allocate any additional stuff to store the large value. So that's the flaw about this program. But hey, it's a working multiplication division program. So now you can, look at the loop a little bit in a different lens, because in the past we did a very simple loop, but in this one it's a little bit more complex, and we actually implement do while with the nested if. So you can see that section and how we create those. All right. Any other questions for me? Aren't you guys happy that we have a holiday and it's tomorrow is basically weekend for everybody, but I gotta work all day tomorrow. So if you're finished, you can put in your name in the chat. I'll stick around for questions. And like I said, okay, my code, you might write it better. So practice doing your own program. I suggest that's how you're gonna get better with LC3. Because all right. Good night. If you're done, have a wonderful night. I'll stick
All
around for
right.
questions. Yes, bye. Yes.
All right. See you next week.
All right. Take care. Thank you.
I actually had a quick question.
Yes.
When you're doing like the first loop in the mult sub function, like you nodded it, or you choose complement, like right underneath the store.
Yeah, so let me share it. Okay. So are you referring to loop, this one
No, the one right above it, the little block on top of it. Yeah.
right here? Okay.
What's the purpose of that?
So remember that we talked about how when y is negative, we're gonna still treat it as positive, but we're gonna assign it later. Okay, I'm gonna show you where that is
Yeah,
in R.
I remember you saying that, like at the end of the.
Right here. See, this is right here. We have to convert it because if you think about it, right? If you have like 4 times a -1, it is -4, right? So if you remove the sign, it's still a 4. Okay? Understand? So if we get rid of this, we still have the value, but we're going to bring it back by doing 2 complement of it. So you basically convert that and check it and make it a positive, but then later on, if it's you check if it's negative, then you are going to make it a 2 complement, because anything multiple, when you multiply, you still have the same value. The only thing is that you have a sign in the front if y is negative.
But
So when you multiply, you're still going to have the same data, but we would then treat the sign as a separate process.
right there, isn't it turning it like to a negative to begin with, even though it's not?
What do you mean?
Like it's going into that mult function,
Uh-huh.
and it's 2's complementing it. So say if I had like a 4, right? So it's gonna it's gonna become a -4 once it goes into that loop, right?
Well, it doesn't matter whether it's -4 or not, right? So that's what it's saying, is that whatever your y is, it's going to convert it to positive because it still is the same value. And then later on, then we would then sign it. Because if you think about, like, if you're saying 4 times 1 is 4, 4 times -1 is 4 with a sign. That's
Yeah,
what it's saying.
it's the same.
So
It's the same
so
value.
if you have a negative y as an input, it's going to convert it to positive, and then it's going to do the multiplication, and then later on it's going to
Switch it back.
it's going to invert it and 2 complement it, so it becomes a negative output.
So that's just for negative numbers to become positive.
Right. And because if you think about the multiplication or the division process, it's still the same as a value. It's just we add the sign to it to indicate that the input is negative for y.
Right. But then why does it go, like, say if I put in a y, the first thing it's gonna do is gonna go into the 2 complements. Then why is it the opposite?
Well, because if you have a negative y, you 2 complement it, you make it into a positive.
But what if I had a negative already? It's gonna be positive.
Yes. So here is where we have to force it to check positive. Which one is this? Sorry. Okay. Let me go to the image. I think I have the image set up. Okay. Right here, right? Now, remember that your y doesn't change because register 2 hold the y. We're reusing that. But for the 4, if you have negative to start with, it's going to convert it to positive.
Right. So
And it will check it for positive. Right?
yeah, then it's gonna go to a positive loop.
Yeah, so it says for the negative values, then it would check for positive. So now, if it's a negative value, then what will happen is it will not check for positive. Okay, so let's think about that. If you have a y like a 1, okay, you copy that over to register 4, unite it, make it -1. Here is where it becomes -1. If it will not check for positive here, it would be false here. So it would not go to this loop. It would just go to the next loop. Understand?
Yeah.
Yeah. So if I start out with y as a positive value, right? I two complement it. If it's a 1, then I make it -1. When it checks R4, if it's a -1, it would not check true for positive here. It's going to skip this positive loop and it's going to go to the next line. Okay. So it doesn't really matter if it's positive. That's what we're saying. It only we use pos loop here to convert it to positive. So that's why we add that here. Okay? Because if it's positive to start with, it's going to skip that positive loop in general. It doesn't need to convert it anymore.
Okay.
I'm sensing you're not getting it.
Well, I got a little bit lost at the very end, like what you just said, like last
Okay.
last sentence. You said it's gonna skip if it's already positive, right?
Yeah, so if it's positive, if it's negative, it's gonna skip pos loop. It's gonna skip this section, and then it's gonna go to the next loop, which is this loop. It's gonna
Right.
go to the next line, and it's gonna do this, right? So then we would then check the other conditions for multiplication and then return. But so if it's already positive, we don't need to convert positive, right? That's what I'm saying is that if it's positive, we don't need to send it into a positive loop. We only need to convert it if it's negative, because positive and negative in the multiplication and division, it's still the same data. But the only thing that's different with the negative input is that we have a sign value, which we handle later on.
Right. So you're just kind of like working backwards then.
Yes.
Yeah. Okay.
Yeah, because if you do that at the beginning, it's gonna tweak all of the subsequent outcome, because you have to do the do while and then you're gonna nest the if in there. So we would check for the if later on by branching it down here, right? After you multiply everything, and then you would then do the quit to is when we convert it for the sign.
Oh, okay. Okay.
Yeah, because it says in negative after they multiply, right? This is where we sign it right here. Because think about the process, right? The computer is designed to be mimicking human. When you multiply in your head, when you do a 3 times a -1, you still think about 3 times 1, correct? That's 3, right? And then after that, you put a sign in the front.
Okay. Okay.
So the processor, the way that we design the instruction is we subsequently put in the subtask to really look at how that would be. We sign it at the end when we write out the output, right? That's what you do when you multiply in your head or you divide, because you divide in positive number because you learn your timetable that way, right? So at the end you sign it, and that's what we're doing that.
Okay. That
It's a
makes
little tricky, but I hope that you see it. And if you're not, then you should put in the value as you work through the register. You can print it out, handwrite it, and so that way you can see why it's doing that. And there's a reason why we branch for a certain section.
okay. Yeah. I'll try to see when I typing it up, see how it goes.
Right. Right. Use it with the input, like register 1 is, put a number, an arbitrary number in there so you can see.
Okay, I will. Thank you for explaining that.
Yeah, no
It helped.
problem. Any other questions? I'm gonna stop recording.